Hey folks, today we'll be writing our own math.square root function without making use of anything from the Python's math library. So here I'll give you a quick demo. This is my function, this is the function from Python, and I will run the code, and you will see that my results are actually very similar to Python's result. And let's take a look at another example. So if I did find and replace, and I replaced 2 with 5, so now we're finding the square root of 5 instead of the square root of 2. And if I ran this again, see that our approximation is very close to whatever Python gives us from the standard library. So how is this accomplished? Well, if I expanded my implementation here, I want you to start on line 10 over here. So this is our initial guess. It's a random shot in the dark. We say maybe the answer is something like 1. Well, obviously the answer isn't 1, but we'll start with a guess. And then now we specify a number of iterations. I picked 50 out of randomness, but you could have done 7 or 10 and it would have worked the same. So then you iterate through the number of iterations and you get a better and better approximation every time you do this iteration. So the larger your number of iterations, the better your approximation is. And I can even show you what this looks like by uncommenting out that line, and I will also change this to something like 7. It's more reasonable so it doesn't blow up my console. So now if I run this again, you'll see that we started off with 1, then our next guess was 1.8, then 1.9, then 2, and we slowly but surely approach a more and more accurate result. And we call this the Newton's method, and it is invented by none other than Isaac Newton himself. We are given a curve that looks like this. This curve resembles the curve of y equals to x squared, so this is your quadratic function. So the goal today is we want to find the x value when y equals to 0. Now there are two x values that you'll get when you set y equals to 0. There's one over here, that's the negative root, and there's one over here, and that's the positive root. Just for argument's sake today, let's just say this positive root is what we want to get. The way you do this is you start with an initial guess. Say today I was feeling a little dizzy and I got a really pretty bad guess, and I guessed that x equals to 10. Now if I went to the graph and I plotted out x equals to 10, this is where that point is, and who knows what y value this is. This is a y value that is definitely not 0. So how do we get closer to this point? Here's the fun part. First, you draw a tangent line, and you can draw the tangent line using derivatives. The first order derivative gives you the tangent line at this given x coordinate. So now this derivative line goes all the way down and it intersects the x-axis at a certain point. Now this is y equals to 0, correct, but it is a point that does not lie on the curve, so it can't be our right answer. But we are closer to our final target. We're just not quite there yet, and we're also not on the curve, which is a requirement. So what I do next is I get rid of this tangent line. So now I have my new point. I will draw a line that goes directly upwards. This is not the same as a tangent line, and I will eventually intersect back at the curve. So now I've got this point, and this point is closer to our target point than our initial guess was. This is the initial guess. So that's just after one iteration. We can do this many iterations, and that's the beauty in Newton's method. What that looks like is we'll draw another tangent line, this time to this closer point, and you see that this tangent line now intersects the x-axis even closer to our target root. Then we repeat the process. We draw a vertical line straight upwards, so we get rid of this old tangent line. We have our next target point, which is even closer to our final target than we previously were. And the secret is to just iterate through this 6 or 7 times until a certain threshold. But why is this so important? Why do we even care about Newton's method? Well, here's why. Imagine you're walking down and it's a regular day. You're going to get ice cream in the ice cream truck, and your professor, your math professor, is standing in front of you in line. He turns back and asks you, "Hey, I have this equation here, okay? Well, if I gave you x equals to 2, you'd be able to solve for y very easily. You'll just say, if x is 2, x squared is 2 squared, so y equals to 4. No problem. You can write a very simple Python one-liner to do this. Here's the kicker. Imagine the prof instead gives you the value of y instead of the value of x, and the value of y happens to be 2. So now you have to solve for x. So when y is 2, what is x squared? And so what is x? So all of a sudden, everyone stops laughing because it's not as funny anymore. Now it's a bit harder. So what you can do is this, and you take this 2 and you move it over to the other side of the equation. X squared minus 2 equals to 0. And this looks very familiar. This looks like a quadratic equation, and I'm just finding the roots of this quadratic equation. And we actually have a special name for this type of root. We call this the square root because this is the power of 2. And the reason why I had to do this special magic trick was because if you look at the regular graph of a square root, it looks like this. That's the square root graph. And this is the root over here. Now, how do I get to that root? If I start with an approximation, if you look at Newton's method, you draw a tangent line, we end up with a point that leads to nowhere, because this is the point right here. If I draw a line upwards, I will never intersect the graph because that goes to infinity. But now that I've done this magic, I've rewritten it so that this is a quadratic equation and we're just finding the roots of that quadratic equation. I can actually just erase this graph, and now I can draw this instead. And the reason I can draw this is because this is a quadratic equation and we're translating it downwards by 2 units. That's the negative 2y direction. And now we have our 2 roots, and if we're interested in the positive root, we can just set our initial guess to x equals to 1 and then perform Newton's approximation method, and we'll eventually get to some number close to this target root, which is the square root of 2, because I can actually just move this 2 over to the other side of the equation and make that x equals the square root of 2. So now let's define some fun mathematical equations we can use to write in terms of computer code. We are given the current guess of x, which we have denoted with x sub n. That's our current guess. But we can do better. The next guess after one iteration will be x sub n plus 1. That's the better guess. That's the next guess. So recall that the derivative of f of x at a given x is equal to the gradient of the tangent line. And this tangent line is tangent to the curve at this point, which is the current guess. We denote the derivative of fx to be f prime x. So this is the derivative. And what is the equation of the derivative? Well, it's delta y over delta x, because that's the gradient of the line. So what is delta y? Now, delta y is just this line over here. But what's the length of this line? Well, because this is y equals to 0 over here. This is the x-axis. So the height of this line must be equal to the y-coordinate of this point. And the y-coordinate of this point is equal to f of x, which is x sub n, because that's the current x. That's why we have delta y equals to that value over there, which is f of x sub n. Now, what is delta x? So this is delta y. What is delta x? Now, delta x is the difference in x. So this is the current x, this is the next x. What is the distance? Well, the distance is the difference, which is subtraction. Very easy. So this x sub n minus x sub n plus 1, that's the length of this line, that's delta x. So now, all we gotta do is, because we already know what the current guess is, let's say the current guess is an arbitrary value, something like 1. So how do we get the next x value, which is the next guess? So we solve this equation, and we solve for this component over here, which is x sub n plus 1. And we finally get the equation in terms of the next guess, which is x sub n plus 1. Also, all the math done here is all on Wikipedia. So if you just go on Google, search Newton's method, you'll find all the rigorous proof all complete on Wikipedia.